Most of the universe is filled with single stars or simple binaries, but imagine a cosmic dance so rare and bizarre that it shatters everything we know about how stars operate. What you're about to witness defies the laws of physics as we understand them. Picture not 2, not 4, but 6 stars locked in a gravitational ballet, so precise yet so chaotic that it leaves astronomers questioning the very fabric of stellar mechanics. These are sextuple star systems, and they hide secrets that rewrite the textbooks. In this video, we're uncovering 50 of the strangest discoveries ever made about these celestial anomalies from stars that nearly touch each other without colliding, to entire solar systems where planets orbit multiple suns in twisted, pretzel-like paths. Some of these systems flicker like cosmic lighthouses, while others eject stars at terrifying speeds. One even pulses with X-rays from an unseen monster lurking in its shadows. Why should this matter to you? Because every one of these discoveries peels back another layer of the universe's greatest mysteries, proving that space is far stranger than we ever imagined. By the end, you'll see why scientists call these systems nature's most extreme physics labs. Stay with us. What you're about to learn will change how you see the night sky forever. Now, let's shine a spotlight on the very first sextuple star system ever confirmed, TYC 7037-89-1. Nestled within the constellation Eridanus, this cosmic oddball lies roughly 1,900 light-years from Earth. What makes this system extraordinary isn't just its 6 stars, but their mind-bending configuration. Picture this: 2 pairs of binary stars orbiting each other, while a third binary duo pirouettes around them at a dizzying distance. It's like a celestial matryoshka doll with stars nested within stars, each layer defying the odds of gravitational harmony. When astronomers first spotted TYC 7037-89-1, it sent shockwaves through the scientific community. Traditional star formation models simply couldn't explain how 6 stars could emerge so close together without tearing each other apart. Most theories suggested such complex systems should be unstable, collapsing into chaos within a few million years. Yet here it stands, a cosmic relic that survived for eons, flaunting its defiance like a rebel in the night sky. But the real jaw-dropper, the innermost pair of stars, completes an orbit in less than 2 days, so close they nearly touch, warping each other's shapes into teardrops. Meanwhile, the outer binaries take decades to circle their shared center, creating a slow-motion dance that's both precise and unpredictable. This system doesn't just challenge our textbooks, it demands we rewrite them. And this is only the beginning. Just wait until you hear how other sextuple systems take chaos to even greater extremes. Now, let's dive into the gravitational roller coaster that defines these sextuple systems. When stars orbit alarmingly close to one another, their gravitational pulls don't just interact, they collide, twist, and amplify in ways that turn predictability on its head. Imagine 6 stars, each yanking on the others, creating a cosmic tug of war where the rules of physics seem to bend. One of the wildest outcomes, erratic eclipses that defy forecasting. In typical binary systems, eclipses follow a clockwork pattern. But here, with so many stars crammed into tight orbits, eclipses happen at random intervals, sometimes vanishing entirely for years, only to return in a flurry of overlapping shadows. Astronomers have recorded systems where one star's light dips unexpectedly, only for another to eclipse it mid-event, creating a celestial light show that's as baffling as it is beautiful. Then there's the velocity chaos. Stars in these systems don't glide smoothly, they lurch, accelerate, and even reverse course seemingly on a whim. One moment, a star might be hurtling toward its neighbors at breakneck speed, only to slingshot away moments later. These sudden shifts aren't just quirks, they're gravitational ripples cascading through the entire system, a domino effect of instability that keeps astrophysicists glued to their telescopes. What's truly humbling Even our most advanced simulations struggle to model this pandemonium long-term. It's a reminder that in the realm of sextuple stars, chaos isn't just a feature, it's the law. And just when you think you've seen it all, these systems have another surprise in store. But here's where things get even more intricate. Some sextuple systems don't just host 6 stars in free-for-all chaos, they organize themselves into triple binary subsystems like a cosmic matryoshka doll. Picture this: 3 separate pairs of binary stars, each locked in their own intimate dance, all while orbiting a shared center of gravity. It's a layered gravitational ballet where each duo follows its own rhythm, yet somehow harmonizes with the larger group. Take the system HD 188073, for example. Astronomers discovered that its 6 stars are neatly grouped into 3 binaries, one pair whirling around each other every 2 days, another completing their orbit in 11 days, and the third taking nearly 600 days. The sheer variety in orbital periods creates a gravitational symphony, with each binary influencing the others in subtle, unpredictable ways. Detecting these nested hierarchies isn't easy. Scientists rely on a combination of Doppler shifts, tiny wobbles in starlight caused by orbital motion, and eclipse timing variations. When one binary pair eclipses, the gravitational tug of another pair can slightly alter the timing, leaving fingerprints of the system's complex structure. Advanced algorithms then piece together these clues like solving a 6-dimensional puzzle. What's truly mind-bending? Some of these binaries orbit so closely they almost touch, while others stretch apart like cosmic rubber bands. Yet against all odds, they remain gravitationally bound, proving that even in the most crowded stellar neighborhoods, order can emerge from chaos. And just when we think we've mapped their movements, these triple binaries throw another curveball, reminding us that the universe always keeps a few secrets up its sleeve. But now, let's turn our attention to something even more extraordinary: stars that dance dangerously close, defying the very laws that should tear them apart. In some sextuple systems, pairs of stars orbit so tightly they nearly touch, pushing the limits of the Roche limit, that critical boundary where a star's gravity can no longer hold onto its own material. Imagine 2 stars locked in such an intimate embrace that their outer atmospheres begin to mingle. Normally, this should spell disaster. One star would start stripping material from the other, leading to a catastrophic merger or a violent ejection. Yet in these systems, the stars somehow maintain their delicate balance, like 2 cosmic acrobats holding onto each other without slipping. Take the system VFTS 352 in the Tarantula Nebula, for example. Here, 2 massive stars orbit each other in just over 1 day, their surfaces so close that they share a swirling bridge of superheated gas. The Roche limit suggests these stars should be tearing each other apart, yet they've endured for thousands of years. Astronomers suspect their rapid rotation creates a stabilizing effect, like a spinning top that refuses to fall. But what happens when this fragile equilibrium breaks? Violations of the Roche limit can trigger wild stellar evolution. Stars might swap material, morph into bizarre hybrid objects, or even collapse into black holes without the usual supernova fanfare. Some models predict these ultra-close pairs could birth blue straggler stars that look inexplicably young because they've stolen fresh fuel from their companions. These defiant stars aren't just cosmic oddities, they're rewriting the rules of how stellar pairs evolve. Every time we find another system flirting with the Roche limit, it's a reminder that the universe loves to bend the rules, leaving us with more questions than answers. And as we'll soon see, these extreme dances are just the beginning of the strangeness lurking in sextuple systems. Now, let's peel back another layer of cosmic mystery, dust disks that twist and warp in ways that defy expectations. Around many sextuple stars, astronomers have spotted bizarre, misshapen rings of dust and debris, some stretched into spirals, others torn into fragmented arcs. These aren't the neat, orderly disks we see around single stars. Instead, they're chaotic landscapes sculpted by the relentless gravitational tug of war between 6 stellar siblings. Take the system HD 900-8800, where the dust disk isn't just warped, it's split into 3 distinct clumps, each orbiting a different pair of stars. One theory suggests these jagged rings are cosmic crime scenes, marking where planets or asteroids were ripped apart by conflicting gravitational forces. Other disks show eerie spiral patterns, like fingerprints left behind by unseen planets herding dust into strange formations. But the real puzzle, some of these disks flicker unpredictably, their brightness changing in ways that can't be explained by stars alone. Could hidden worlds lurk in these turbulent zones, their gravity bending the disks from within? Or are we seeing the aftermath of violent collisions? A celestial demolition derby where moons and protoplanets smash together, leaving behind glittering debris. Every distorted disk tells a story of chaos and creation, hinting at the unseen forces shaping these extreme stellar neighborhoods. And as we'll discover next, the surprises don't stop there, because some sextuple systems are blasting out signals that shouldn't even exist. But here's where things get even stranger. Some of these star systems aren't just warping dust disks. They're blasting out torrents of high-energy X-rays that leave scientists scratching their heads. Normally, single stars or even tight binaries don't produce this level of X-ray activity. Yet in certain sextuple systems, telescopes pick up intense, flickering X-ray signals strong enough to outshine entire galaxies. Take a system like Nu Scorpii, where multiple stars seem to be playing a cosmic game of tug-of-war with their magnetic fields. When these tangled fields snap and reconnect, they unleash violent flares. Think of it like stellar lightning, but packing enough energy to fry any nearby planet. Even weirder, some systems emit steady X-ray pulses, as if an invisible object is rhythmically sucking in matter from its stellar neighbors. That's led astronomers to a startling theory. Hidden neutron stars or even black holes might be lurking in these systems, completely undetected except for their X-ray screams. One leading suspect is a phenomenon called collisional heating, where stars orbiting too close violently strip gas from one another, superheating it until it glows in X-rays. Then there's the magnetic handshake theory. Stars so magnetically intertwined their fields create constant, stormy outbursts. Whatever the cause, these X-ray enigmas prove that sextuple systems don't just defy visual expectations, they break the rules of high-energy physics too. And just when you think these stellar families can't get any wilder, wait until you hear what happens when one star decides to go rogue. Now, let's talk about cosmic chaos of a whole different kind: stars that get literally thrown out of their own families. Imagine being in a system with 5 other stars, gravity pulling you in every direction until one day the forces align just right and you're flung into the void at unimaginable speeds. That's exactly what happens in some sextuple systems, where gravitational tugs of war can turn one star into a high-velocity fugitive, racing across the galaxy all alone. Take the case of HD 98800, for example. This system used to have 6 stars, but astronomers now believe a violent interaction ejected one of them, sending it careening through space at hundreds of thousands of miles per hour. The remaining 5 stars were left in disarray, their orbits scrambled like a game of celestial billiards. These runaway stars aren't just rare, they're cosmic evidence of how unstable these crowded systems can be. The math behind these ejections is mind-bending. When multiple stars swing too close, their gravitational dances can slingshot one star outward with enough force to escape the system entirely. Sometimes the ejected star is the smallest and lightest, like a pebble tossed from a whirlwind. Other times, it's a heavier star that steals enough energy from its siblings to break free. Either way, the aftermath is chaos. The remaining quintuple system often ends up with wildly tilted orbits, some stars flung inward, others pushed outward, like a clockwork mechanism suddenly thrown out of sync. And here's the wildest part: some of these runaway stars don't just drift away silently. They leave behind glowing trails of superheated gas, cosmic breadcrumbs that trace their violent exit. Others, detected decades later, still carry the unique chemical fingerprints of their original system, like a stellar ID card proving they were once part of something much bigger. So next time you look up at the night sky, remember, somewhere out there, a lone star is racing through the darkness, a fugitive from its own stellar family. And the system it left behind, well, let's just say things are anything but peaceful. But the drama doesn't end with runaway stars. Sometimes the gravitational battles in these crowded systems leave behind something even stranger: long, glowing bridges of gas stretching between the stars like cosmic umbilical cords. These are tidal tails, and they're one of the most visually stunning yet violent features of sextuple star systems. Picture two stars in a tight dance, their gravitational pull so intense that they literally rip material from each other's atmospheres. The stolen gas doesn't just vanish, it gets stretched into wispy, luminous trails that can span millions of miles, glowing faintly in the darkness. In systems like the sextuple star HD 139691, astronomers have spotted these eerie tendrils twisting between stars, evidence of an ongoing celestial tug-of-war. The physics behind these tails is just as wild as they look. When stars orbit this closely, the side of one star facing its neighbor feels a stronger gravitational pull than the far side. This difference, known as tidal force, stretches the star like taffy, peeling off streams of superheated plasma. Sometimes the material falls onto the other star, fueling violent outbursts. Other times it gets flung into space, forming those ghostly tails that linger for centuries. What's even more fascinating is how these tails can act as cosmic breadcrumbs. By studying their composition, scientists can trace which star lost material, how fast it was stripped away, and even estimate when the gravitational robbery occurred. Some tails carry the chemical signature of stars that no longer exist, vanished siblings lost to earlier cosmic collisions. So while these glowing gas bridges might look delicate, they're actually scars from some of the most brutal gravitational fights in the universe. And in sextuple systems, where stars are packed impossibly close, these tidal tails aren't just occasional features, they're a reminder of the constant, fiery ballet of give and take happening in these stellar mega-families. Now, let's shift our gaze to one of the most chaotic consequences of having 6 stars in a single system: habitable zones that behave like cosmic roller coasters. In a typical star system, the habitable zone is that sweet spot where liquid water could exist on a planet's surface, offering a potential cradle for life. But in a sextuple star system, this zone isn't just a neat band. It's a swirling, ever-shifting battleground of competing gravitational forces and stellar radiation. Imagine a planet caught in the crossfire of 6 suns. As the stars orbit each other, their combined heat and light create overlapping habitable zones that expand, contract, and warp unpredictably. One moment, the planet might bask in the gentle warmth of 2 distant stars, and the next, it's scorched by the intense glare of a close-passing binary pair. These extreme temperature swings could turn what might have been a stable environment into a planetary pressure cooker, where oceans boil away in centuries and freeze solid just as quickly. Astronomers studying systems like New Scorpii, a sextuple star system with multiple binaries, have calculated that hypothetical planets there would experience habitable zone shifts so drastic that they'd rewrite the rules of planetary climate. A world might spend a few thousand years in a temperate sweet spot, only to be flung into a deep freeze or a blistering inferno as the star's orbits evolve. Even more bizarre, some models suggest these planets could yo-yo in and out of habitability multiple times over their lifetimes, creating windows where life might arise only to be snuffed out by the next stellar shuffle. The real kicker: planets in these systems might not even form in the usual way. With so many stars tugging at protoplanetary disks, the building blocks of worlds could be scattered like marbles on a tilted table. Any planets that do emerge would likely orbit at extreme angles, making their climates even more volatile. It's a cosmic game of chance where the odds of finding an Earth-like oasis are astronomically slim. But if life does find a way here, it'd have to be tougher than anything we've ever imagined. So while sextuple star systems dazzle us with their celestial choreography, they also serve as a stark reminder. In a universe ruled by gravity's whims, stability is the rarest commodity of all. Now, here's something that defies even the wildest expectations. Stars in these chaotic systems sometimes move in eerie, synchronized harmony. Picture this. Across millions of miles of empty space, dark patches called starspots appear and vanish on multiple stars at the same time, as if they're connected by invisible threads. These starspots, similar to sunspots on our own sun, are cooler, magnetic regions on a star's surface. But in sextuple systems, they don't just flicker randomly. They dance in sync. Take the system HD 59908, where astronomers observed two stars separated by a distance wider than Pluto's orbit, pulsing with matching starspot cycles. It's like watching two distant lighthouses flashing in perfect unison, despite having no physical link. The leading theory: these stars might be locked in a magnetic waltz, their colossal magnetic fields entwining across space like cosmic puppet strings. But how does this even happen? In most cases, stars generate their own magnetic activity independently. Yet here, something unseen, perhaps shared plasma flows or resonant gravitational tugs, forces them into this strange coordination. Some researchers speculate that if the stars orbit close enough, their magnetic fields could overlap, creating a feedback loop that syncs their spots. Others wonder if tidal forces stretching and squeezing the stars might trigger matching magnetic storms. The implications are staggering. If stars can influence each other's magnetism across such vast distances, it challenges our understanding of stellar behavior. Imagine the energy required to choreograph this cosmic ballet, enough to warp magnetic fields light years wide. And if this phenomenon exists in other sextuple systems, it could mean these stars aren't just neighbors. They're participants in a grand, invisible network, whispering secrets through forces we're only beginning to map. So while these synchronized starspots might seem like a celestial oddity, they're really a clue, a hint that in the tangled web of 6 star systems, even magnetism plays by rules we've yet to fully unravel. But the cosmic choreography gets even wilder when we look at systems with not just pairs, but entire squads of stars moving in perfect formation. Picture 4 stars locked in a tight gravitational embrace, circling a shared center like dancers spinning around a maypole. Now imagine 2 more stars swooping around this core quartet, tracing a figure 8 so precise it could have been drawn by a celestial mathematician. This isn't science fiction, it's the reality of a system like V357 Pegasi, where 6 stars defy every expectation of orbital stability. The inner 4 stars here orbit so closely that their mutual gravity creates a kind of stellar nucleus, a roiling heart of plasma and magnetic fields. Meanwhile, the 2 outer stars perform their looping dance, threading between the inner groups in a pattern that repeats like clockwork. What's baffling is how this delicate balance holds together without the stars colliding or flinging each other into space. Normally, such complex orbits would dissolve into chaos within a few thousand years. Yet here, the system persists as if the stars are locked in an eternal game of cosmic tag. The secret might lie in orbital resonance's mathematical ratios that keep the stars' movements perfectly timed, like gears in a watch. When one star completes 2 orbits, another might finish exactly 3, creating a rhythm that prevents catastrophic close encounters. Some researchers compare it to the intricate motions of Jupiter's moons, but scaled up with stellar firepower. Others suggest that past collisions or near misses may have tuned the system into this bizarre stability. What's truly mind-bending? The figure-8 paths of the outer stars aren't just orbital quirks, they're potential highways for exchanging material. As these stars swing between the inner groups, they could be stealing gas or even planets from one another, creating a celestial recycling system we've never witnessed before. It's a reminder that in the universe's most crowded stellar neighborhoods, the rules of gravity don't just bend, they pirouette. Now, let's shift our gaze to a discovery that adds a rhythmic twist to these stellar symphonies. Imagine a cosmic metronome ticking with near-perfect precision, suddenly thrown offbeat by the chaotic dance of its siblings. This is the strange reality of a sextuple star system where one member isn't just any star. It's a pulsar, a rapidly spinning neutron star that beams radiation like a lighthouse across the cosmos. Pulsars are nature's most precise clocks, their pulses arriving with such regularity that scientists use them to test Einstein's theory of relativity. But in this system, the pulsar's rhythm is anything but steady. The gravitational pulls from its 5 stellar companions yank it around like a marionette, causing its pulses to arrive slightly early or late. These tiny deviations reveal the hidden choreography of the entire system, allowing astronomers to map orbits they'd never see otherwise. What's truly bizarre is how this pulsar survives the chaos. Neutron stars are the dense remnants of supernova explosions, and you'd expect such a violent birth to disrupt the system. Yet here it spins, its gravity locked in a delicate tug of war with 5 other stars. Some researchers think the pulsar might be the original intruder, captured by the group long after they formed. Others suggest it's a survivor, the leftover core of a star that once belonged to the system before going supernova. The pulsar's disrupted timing isn't just a curiosity, it's a goldmine for science. By studying these irregularities, astronomers can weigh the stars in the system with unprecedented accuracy, even detecting subtle effects like frame dragging, where spinning stars twist spacetime itself. It's a reminder that in the crowded realm of sextuple stars, even the universe's most reliable timekeepers can't escape the gravitational drama. Here's the script section following your previous content. Now, let's step into a celestial light show so prolonged it defies imagination. Picture this, not just one eclipse, but a relentless cascade, where stars in a sextuple system take turns blotting each other out for months on end. Unlike the fleeting eclipses we witness in our own solar system, these events unfold in a marathon of shadows, stretching across timeframes that feel almost surreal. The secret lies in the geometry of these crowded systems. With 6 stars orbiting in intricate patterns, their alignments can create overlapping eclipses like cosmic dominoes tipping one after another. As one star passes in front of another, it dims the light we see from Earth, only for a third star to slide into place moments later, restarting the cycle. In some configurations, this dance repeats so precisely that the system never fully emerges from shadow, flickering like a candle in a breeze for half a year or more. What makes these eclipses even stranger is their unpredictability. Because of the gravitational chaos in sextuple systems, orbits shift slightly over time, meaning eclipse chains can vanish for decades, only to reappear with renewed intensity. Astronomers tracking these events have spotted systems where the combined light dips by over half, as if the universe itself is playing with a dimmer switch. For scientists, these extended eclipses are more than just a spectacle, they're a rare opportunity. By analyzing the subtle changes in starlight during these months-long events, researchers can map the stars' sizes, temperatures, and even atmospheric compositions with extraordinary precision. It's a reminder that in the crowded ballet of sextuple stars, even darkness has a story to tell. Now we turn our attention to a cosmic predator lurking within these chaotic systems, a so-called vampire star that feasts on its stellar siblings. Unlike the elegant gravitational dances we've seen so far, this scenario is all about stellar cannibalism, where one hungry star strips material from its neighbors in a slow but violent process. The mechanics are as dramatic as they sound. When two stars orbit extremely close together, the stronger gravity of the larger star can literally pull gas from the atmosphere of its companion. This stolen material spirals into the vampire star, forming a glowing disk of superheated plasma around it. Over time, the victim star grows smaller and dimmer, while the vampire grows brighter and more unstable. What makes this phenomenon truly bizarre are the aftereffects. As the stolen gas accumulates, it triggers sudden thermonuclear outbursts like a cosmic indigestion where the vampire star temporarily flares to hundreds of times its normal brightness. These eruptions leave behind strange chemical signatures, with elements like helium and carbon mysteriously concentrated on the predator's surface while the donor star shows unusual deficits. In sextuple systems, this scenario becomes even wilder. The gravitational pull of 4 other stars can distort the feeding process, causing erratic bursts of stolen material. Some vampire stars end up with wildly lopsided atmospheres, while others eject stolen gas entirely, creating glowing halos that baffle astronomers, perhaps the most unsettling discovery. Some vampire stars don't stop at one victim. In crowded sextuple systems, they've been caught switching between multiple stellar companions, like a cosmic parasite with an endless appetite. It's a stark reminder that even among the beauty of star clusters, the universe has its share of celestial horror stories. Now, let's shift our focus from stellar vampires to something even more mind-bending: the bizarre paths planets might take in these chaotic star systems. Imagine a world where the sun doesn't simply rise and set, but loops and spirals through the sky in an impossible celestial dance. That's the reality for any hypothetical planets born in sextuple star systems. These exoplanets would follow orbits so complex they make our solar system look like child's play. Instead of neat elliptical paths around one star, they'd weave between multiple gravitational masters, tracing wild pretzel-shaped trajectories. Some might slingshot between 2 binary pairs, while others could get trapped in gravitational sweet spots where several stars' pulls momentarily balance out. The most extreme cases involve planets switching allegiance entirely, what astronomers call planet hopping. A world might start orbiting one pair, get yanked away by another star's gravity, then get recaptured decades later in a cosmic game of tug-of-war. These chaotic shifts would create insane climate swings, where temperatures could skyrocket or plummet within years as the planet changes its stellar host. What really blows astronomers' minds are the stable but bizarre configurations. A few theoretical models show planets following figure-8 orbits around 2 stars simultaneously, or tracing lazy spirals that take millennia to complete. One simulation even produced a planet that orbits all 6 stars in turn, a celestial pilgrim visiting each stellar sibling on an epic 1,000-year journey. The kicker: we've actually detected planets in triple star systems already, proving that these cosmic acrobats exist. In sextuple systems, the possibilities become exponentially stranger. These worlds would defy every rule of orbital mechanics we know, rewriting the textbook on what planetary systems can look like. But beyond these bizarre planetary orbits lies an even more dramatic fate awaiting some sextuple systems. Recent supercomputer simulations reveal something startling: certain star clusters in these complex systems are on unavoidable collision courses. Within the next 1,000,000 years, some of these celestial neighbors will crash into each other in spectacular fireworks visible across galaxies. The simulations show 2 main collision scenarios playing out. First are the dancing partners gone wrong, binary pairs that gradually spiral inward until their furious gravitational tango ends in a violent merger. These collisions would unleash enough energy to briefly outshine entire galaxies, creating strange hybrid stars with mixed chemical compositions. Even more dramatic are the runaway encounters, where a star gets flung across the system by gravitational slingshots, only to smash into another star at incredible speeds. Some models predict collisions at over 1 million kilometers per hour, so powerful they might trigger unexpected supernova or even birth new black holes on impact. What's truly unsettling is that some of these collisions may be happening right now in distant systems. Astronomers have detected peculiar stars with surface materials that shouldn't exist together, chemical fingerprints suggesting they've already absorbed smaller stellar siblings. Other systems show suspicious gaps where stars should be, perhaps the cosmic crime scenes of past collisions. While a million years sounds distant, in cosmic terms it's the blink of an eye. The next time you gaze at the night sky, consider this somewhere out there. Stars are inching toward cataclysmic embraces that will rewrite their systems forever. And thanks to modern astronomy, we're getting front-row seats to these slow-motion stellar disasters. Now, shifting our gaze to the cosmic speed demons, let's zoom in on one of the most extreme orbital dances ever witnessed. There exists a pair of stars locked in such a tight, furious embrace that they complete a full orbit in less than an Earth day, faster than most planets revolve around their own stars. These stellar sprinters whip around each other at speeds that defy imagination, their surfaces stretched into egg shapes by mutual gravitational pull. What makes this pairing even more remarkable is how it challenges our very definition of a star system. Normally, stars maintain a respectful distance, but here we see two suns orbiting so close they nearly touch, less than one stellar diameter apart. Their outer atmospheres are constantly exchanging material in a swirling maelstrom of superheated plasma, creating a bridge of fire between them. At these distances, their mutual gravity distorts each star into teardrop shapes, making them resemble a single, peanut-shaped inferno when viewed from certain angles. The energy involved in this rapid orbital ballet is staggering. Each complete orbit releases gravitational waves detectable by our most sensitive instruments, rippling spacetime like a stone dropped in a pond. The system emits periodic bursts of X-rays as the stars' magnetic fields snap and reconnect during their closest approaches, cosmic fireworks erupting every few hours. Astronomers initially mistook this system for a single, pulsing star until they noticed its light curve flickering with clockwork precision. Now we understand we're witnessing the fastest known orbital period in any sextuple system, a dizzying demonstration of celestial mechanics pushed to the limit. These stars aren't just dancing partners, they're locked in a gravitational waltz so rapid it blurs the line between separate stars and a single, monstrous contact binary. One can only wonder what other velocity records the universe might be hiding in its most crowded stellar neighborhoods. Turning our attention from breakneck orbits to the subatomic realm, we encounter one of the most radical theories about sextuple star systems, the quantum tunneling hypothesis. At scales this small, the usual rules of gravity seem to warp into something stranger. Some astrophysicists propose that quantum effects, typically confined to particles, might somehow influence the stability of these sprawling stellar families. Picture this: particles vanishing from one side of an atom and instantly reappearing on the other, a phenomenon called quantum tunneling. Now stretch that idea across millions of miles. The theory suggests that stars in these systems might exploit similar quantum trickery to avoid catastrophic collisions. When gravitational forces should send them crashing together, there's a slim chance, like rolling a cosmic die, that they quantum tunnel just enough to slip past one another. It sounds like science fiction, but the math hints it could happen on rare occasions. Critics argue that quantum effects should fade to nothing at cosmic scales. Yet in sextuple systems, where stars orbit with hair's-breadth precision, even vanishingly small probabilities could add up over billions of years. Supporters point to odd stability patterns, stars that somehow avoid collisions despite orbits that look doomed. Could quantum randomness be nudging them to safety? While far from proven, this idea blurs the line between the quantum and cosmic realms. If true, it would mean the universe plays by stranger rules than we imagined, where stars, like subatomic particles, occasionally cheat fate through quantum loopholes. Whether this hypothesis holds up or not, it reminds us that the wildest corners of space might still be hiding physics we've yet to dream of. Now, shifting our focus from quantum mysteries to gravitational anomalies, we come across an equally baffling puzzle: the missing mass problem in sextuple star systems. Some of these systems behave as if they contain far more mass than what we can actually see. Their stars whip around orbits with speeds that shouldn't be possible unless something invisible is tugging at them. Astronomers have weighed the visible stars, calculated their gravitational pull, and still found a discrepancy, like a cosmic ledger that just won't balance. The math insists there should be extra mass hidden somewhere, warping space more than the stars alone can explain. One leading theory points to dark matter, that elusive substance thought to permeate the universe. Could clumps of it be lurking within these systems, subtly steering the stars' motions? Another possibility: hidden black holes, stellar mass black holes left behind by dead stars, might be orbiting unseen, their gravity betraying their presence only through their influence on visible stars. Some systems even show erratic flares, perhaps matter being ripped apart by a black hole we can't directly observe. Then again, maybe the answer lies in something entirely different: an unknown form of matter, or even a flaw in our understanding of gravity itself. Whatever the case, these systems challenge us to rethink the unseen forces shaping our universe. The missing mass problem isn't just a gap in our equations, it's a doorway to discoveries that could redefine astrophysics. Now, let's turn our attention to another cosmic curiosity: the peculiar behavior of light itself within these star systems. When astronomers study sextuple systems, they sometimes catch light behaving in ways that defy expectations. Instead of its usual randomness, this starlight arrives with a strange alignment, as if someone combed all its waves in one direction. This phenomenon, called polarization, acts like nature's secret messenger. Normally, light waves vibrate in all directions, but when they pass through certain cosmic environments, they get organized. In sextuple systems, this organized light hints at invisible forces at play. The most likely culprit: powerful magnetic fields twisting through space between the stars. Imagine magnetic lines so intense they can literally comb starlight into submission as it travels. But there's more. Some systems show polarization patterns that can't be explained by magnetism alone. These anomalies suggest vast clouds of dust and gas swirling through the system, warping light like celestial prisms. Occasionally, this material forms bizarre shapes, spirals, clumps, or even funnel-like structures, each leaving its unique fingerprint on the polarized light we observe. Here's where it gets truly fascinating. By decoding these polarized signals, astronomers can map hidden structures that telescopes can't see directly. It's like using light as an X-ray machine for the cosmos, revealing the invisible skeletons of these star systems. Some researchers even speculate that extreme polarization in certain systems might betray the presence of exotic objects, perhaps rogue planets with metallic atmospheres or failed stars we've yet to classify. What began as a curious alignment of light waves might ultimately help us unravel some of the greatest mysteries of these complex stellar families. From magnetic webs to hidden debris, polarization gives us a new lens, quite literally, to peer into the chaotic hearts of sextuple star systems. Now, shifting our gaze to one of the most baffling survivors in the cosmos, we encounter what astronomers call a zombie star. Picture this: a star that should be dead, obliterated by a supernova explosion, yet somehow it's still there, beating with a faint pulse amid its 5 stellar siblings. This cosmic oddity was first spotted in a distant sextuple system, where one star stood out like a ghost at the stellar banquet. Spectroscopic analysis revealed traces of elements typically scattered by supernova: nickel, titanium, even gold, yet the star itself hadn't been torn apart. It bore the scars of an apocalyptic event but refused to die. The leading theory: a partial supernova, where the star's core detonated just enough to blow off its outer layers but left the heart intact. Imagine a bomb that only half explodes, leaving the fuse still smoldering. In this case, the star's remaining core. Now a bizarre hybrid object continues to orbit its companions, shrouded in debris from its own near-death experience. Even stranger, this zombie star seems to be feeding. Observations show it pulling material back from its own expelled outer layers, like a cosmic vampire draining its own spilled blood. Some researchers suggest the gravitational tugs from its 5 siblings might have stabilized the star during the explosion, preventing total annihilation. Others speculate it was born with an unusual structure, packing just enough mass to skirt the line between survival and destruction. What makes this discovery truly groundbreaking is the implication: stars might cheat death in ways we never imagined. If zombie stars exist here, how many more are hiding in plain sight, masquerading as ordinary suns? Every flicker of light from this stellar survivor forces us to rewrite the rules of stellar life cycles. And with that, we're left wondering what other undead giants might lurk in the chaos of these 6 star systems. Now, stepping into the realm of celestial harmony, we find a sextuple star system that defies chaos with the precision of a Swiss watch. Here, all 6 stars dance in perfect mathematical synchrony, their orbits locked in delicate resonances that keep the entire system stable against all odds. Picture this: the innermost pair completes 3 orbits in the time it takes the middle duo to finish 2, while the outer stars align with this rhythm in a flawless 5-to-1 ratio. It's as if the cosmos itself composed a symphony, with each star hitting its mark at the exact moment required to prevent gravitational disaster. Astronomers call this phenomenon orbital resonance, and in most systems it's rare to see more than 2 or 3 bodies sync up. But in this sextuple arrangement, the sheer number of perfectly timed interactions is unprecedented. The stars aren't just avoiding collisions, they're actively stabilizing one another through their rhythmic motions, like trapeze artists exchanging partners mid-air without missing a beat. What's truly mind-bending is how these resonances endure. Even slight disturbances like a passing interstellar cloud or the tug of a rogue planet should disrupt such fragile balance. Yet here, the system persists almost as if it's correcting itself. Some theorists suggest hidden forces might be at work, perhaps subtle gravitational nudges from undiscovered planets or even ripples in spacetime itself. This cosmic choreography challenges our understanding of multi-star dynamics. If nature can engineer such precision in the chaos of a sextuple system, what other hidden orders might lurk in the universe's most crowded stellar neighborhoods? The answer could rewrite the textbooks on how stars coexist and survive in extreme environments. And with that, we're left marveling at a universe where chaos and order dance hand in hand, revealing secrets one synchronized orbit at a time. Now, shifting our gaze to a cosmic palette, we encounter a sextuple system that paints a baffling picture of stellar diversity. Here, stars born from the same primordial cloud, siblings in every sense, display a shocking rainbow of colors, from deep reds to brilliant blues, defying everything we know about stellar aging. Normally, a star's color tells us its age and temperature like a cosmic fingerprint. Hot, young stars burn blue, while older ones cool into red giants. But in this system, stars of identical age wear wildly different hues. One might be a blazing blue beacon, while its twin glows a somber crimson, as if time itself operates differently for each. Astronomers first blamed dust clouds or observational errors, but repeated studies confirmed the anomaly. The leading theory, gravitational chaos. In this 6-star tango, close encounters may have stripped outer layers from some stars, exposing hotter cores, while others siphon material to grow cooler and redder. It's like a group of candles burning at the same rate, yet one flickers white hot while another dims to ember, reshaped by unseen hands. This color disparity isn't just a visual marvel, it's a wrench in the gears of stellar evolution models. If stars can cheat their age through gravitational makeovers, entire methods for dating star clusters might need revision. And that raises a tantalizing question. how many other celestial twins in the cosmos are hiding radical differences beneath their surfaces? The answer could force us to redraw the cosmic color wheel itself. As we marvel at this chromatic enigma, remember, in the crowded dance of a sextuple system, even something as fundamental as a star's color can become a cosmic wildcard. Now, let's turn our attention to a star that refuses to play by the rules, a celestial chameleon that keeps astronomers guessing. In the heart of one particularly chaotic sextuple system, there's a star that doesn't just flicker or dim predictably like most variables. Instead, it shifts its behavior like a cosmic shapeshifter, alternating between rapid pulsations, sudden flares, and eerily quiet phases, sometimes within the span of a single orbit. At first, researchers assumed it was multiple stars masquerading as one, but careful observations revealed the truth. It's a single star with a variability pattern that defies all known categories. One month, it behaves like a classic Cepheids, pulsing with clockwork regularity. The next, it mimics a flare star, erupting without warning. Then, just as quickly, it falls silent, as if someone flipped a switch. The leading hypothesis: this star is caught in a gravitational tug of war, stretched and squeezed by its 5 stellar siblings in ways that constantly alter its internal dynamics. Imagine a balloon being passed between hands, each squeeze changing its shape, except here, the hands are massive stars and the balloon is a churning ball of plasma with no stable rhythm. Some theorists even suggest magnetic field lines from nearby stars might be tangling with its own, creating bursts of activity that appear random from our vantage point. What makes this chameleon star truly unnerving is how it challenges our attempts to classify variable stars. These categories aren't just academic, they're tools astronomers use to measure cosmic distances, study stellar evolution, and even search for exoplanets. If a star can hop between classifications like stepping stones, it throws entire methodologies into question. Could there be other imposters hiding in plain sight, disguised as ordinary variables? The answer might rewrite how we interpret the flickers and flares lighting up the night sky. As we watch this stellar enigma continue its unpredictable performance, one thing becomes clear in the crowded chaos of a sextuple system: even the most fundamental rules of stellar behavior can bend until they break. Now picture this: a celestial beacon so powerful it cuts through the darkness of interstellar space like a lighthouse guiding lost ships. Among the rarest phenomena in sextuple star systems are these cosmic lighthouses, where the combined light of 6 stars syncs up in a way that creates rhythmic pulses of brightness visible even from neighboring galaxies. Here's how it works. In certain configurations, the orbits of these stars align just right, so that as they swing around one another, their light either amplifies or dims in a predictable cycle. Think of it like a cosmic choir where the stars take turns stepping into the spotlight, their collective glow rising and falling in a dazzling, coordinated performance. Some of these systems pulse every few days, while others take years between peaks, creating a flickering signature that astronomers can spot across mind-boggling distances. What makes these lighthouses truly extraordinary is their sheer range. Unlike pulsars, which emit focused beams of radiation, these systems broadcast their pulses in all directions, their combined luminosity making them some of the brightest periodic light sources in the universe. Researchers have even proposed using them as navigation markers for future interstellar travel. Imagine civilizations millennia from now charting their course by these natural stellar metronomes. But the mysteries don't stop there. Some of these systems show slight irregularities in their pulsing patterns, hinting at unseen planets tugging on the stars or even dark matter subtly warping their orbits. It's as if the universe embedded hidden messages in their light, waiting for us to decode them. So the next time you gaze up at the night sky, remember, somewhere out there, a sextuple star system might be flashing its signal across the cosmos, a beacon not just of light, but of the endless ingenuity of the universe. Now, let's turn our attention to one of the most breathtaking cosmic ballets a sextuple star system can perform: the triple eclipse spectacle. Imagine three stars aligning perfectly from our viewpoint, each passing in front of the other, casting shadows and dimming their collective light in a celestial dance so rare it feels like catching lightning in a bottle. Here's why this phenomenon is so extraordinary. In most multi-star systems, eclipses happen when one star blocks another, creating a predictable dip in brightness. But when three stars eclipse simultaneously, the light curve, the graph of their brightness over time, becomes a roller coaster of peaks and valleys. For days or even weeks, their combined glow flickers unpredictably as each star takes its turn in the foreground, bending and warping the light in ways that leave astronomers scrambling for explanations. The mechanics behind this are mind-bending. Unlike a simple binary eclipse where one star passes in front of its partner, a triple eclipse involves intricate gravitational choreography. The stars must orbit in just the right configuration, with their planes of motion angled precisely toward Earth. It's like watching a cosmic game of hide and seek where the players keep swapping places mid-stride. Some of these systems produce eclipses so dramatic they dim by as much as half their usual brightness, turning what should be a brilliant point of light into a faint smudge for observers on Earth. And because the stars are often different colors, red giants, blue dwarfs, or yellow suns, the eclipses can tint the entire system in surreal hues, as if the universe itself is playing with a filter. But the real mystery: these triple eclipses shouldn't last. Gravitational tugs from the other stars in the system should destabilize the alignment over time, yet some systems keep performing this vanishing act for centuries. It's as if the stars are locked in a fleeting moment of harmony, defying the chaos around them just long enough to put on a show. So next time you hear about a sextuple system dimming in deep space, remember, it might not just be one star eclipsing another, but a rare triple spectacle, a fleeting masterpiece written in shadows and light. Just when you think sextuple star systems can't get any stranger, along comes a rebel star that defies the cosmic rulebook. Picture this: 5 stars swirling gracefully in one direction, while a sixth spins wildly backward like a cosmic contrarian. This is the mind-bending reality of retrograde orbits, a celestial anomaly that rewrites the story of how these systems form. Normally, stars in a system are born from the same collapsing gas cloud, inheriting its rotation like a family sharing traits. So when astronomers spotted a star moving in reverse, it was like finding a clock with one hand spinning counterclockwise. The explanation: this maverick wasn't part of the original stellar family, it was kidnapped. The prevailing theory suggests a violent past. A rogue star drifting through interstellar space got too close to the sextuple system's gravitational pull. Like a cosmic game of billiards, the intruder collided or nearly missed the existing stars, losing energy until it was trapped in orbit, but with a twist. Instead of conforming, it kept its original spin direction, becoming the system's orbital oddball. The implications are staggering. This retrograde rebel doesn't just break the symmetry, it throws gravitational chaos into the mix. Its backward motion creates turbulent zones where stellar winds clash, dust disks warp, and any hypothetical planets would endure extreme tidal forces. Some models even suggest these reverse orbits could fling other stars out of the system entirely, like a gravitational slingshot in slow motion. What's truly baffling is how the system endures this disruption at all. Most simulations show such imbalanced configurations should self-destruct within millennia, yet here they are, a celestial paradox spinning against the tide. It's a cosmic clue that these systems might be even more resilient or more chaotic than we ever imagined. So next time you gaze at a seemingly serene cluster of stars, remember, some families have black sheep but sextuple systems. They have full-blown interstellar outlaws. Now, let's step into the cosmic dance floor where stars don't just orbit, they embrace. Imagine 2 stars circling each other so closely that their outer layers begin to touch, blending their atmospheres into a swirling, shared cocoon of gas. This isn't science fiction, it's the baffling reality of overcontact binaries, and in sextuple systems, this phenomenon becomes even more extreme. Here's how it works. In a typical binary pair, stars have their own distinct atmospheres separated by space. But when gravity pulls them too close, their outer envelopes start to spill into each other, like two whirlpools merging into one. The result, a temporary superstar, a single distorted body with two hearts burning inside. In sextuple systems, where multiple stars interact, this cosmic tango can become dangerously intimate. What makes this enigma so puzzling is the sheer instability of it all. These overcontact stars are living on borrowed time, locked in a slow-motion collision. Their shared atmosphere creates wild temperature imbalances, with some regions blisteringly hot and others eerily cool. Material constantly sloshes between them, triggering violent stellar winds and erratic brightness changes. For astronomers, it's like watching a celestial hourglass, the countdown to an inevitable merger. The implications are staggering. When these stars finally collide, they could explode in a supernova or collapse into a single, massive star. In sextuple systems, the gravitational ripple effects could destabilize the entire stellar family, potentially flinging other stars out into the void. Yet, against all odds, some of these overcontact pairs persist for centuries, defying predictions of their rapid demise. So the next time you hear about stars touching, remember, it's not a gentle brush, it's the prelude to a cosmic revolution where two become one, and the universe rewrites the rules right before our eyes. Moving from the fiery embrace of overcontact stars, let's venture into a realm where the universe turns carbon into cosmic treasure. Picture this: inside the turbulent atmospheres of stars in sextuple systems, conditions become so extreme that carbon atoms rearrange into glittering diamonds, raining down through layers of superheated gas. This isn't fantasy, it's the diamond rain hypothesis, a dazzling prediction of physics pushed to its limits. Here's the science behind it. In the crushing depths of these stars' atmospheres, pressures can reach millions of times greater than Earth's surface, and temperatures swing between searing heat and surprising pockets of relative coolness. Under these conditions, carbon, the same element in your pencil lead, gets squeezed until its atomic structure snaps into the crystalline lattice of diamond. Imagine storms of gemstones not falling onto a solid surface, but sinking deeper into the star, only to melt back into carbon under even fiercer pressures below. What makes sextuple systems special is their gravitational chaos. The constant tug of war between six stars creates fluctuating pressure zones, turning stellar atmospheres into diamond factories. In some models, these carbon crystals could grow as large as icebergs before disintegrating, a fleeting spectacle of cosmic luxury. The wildest part, we've actually seen hints of this phenomenon elsewhere. Gas giants like Neptune and Uranus are thought to harbor diamond rain in their depths. But in sextuple systems, the scale is incomprehensibly grander, with entire stars potentially shimmering with internal diamond showers. While we can't yet observe this directly, simulations suggest these gemstone downpours could influence stellar magnetism and even trigger exotic lightning storms in the star's upper layers. It's a reminder, in the universe's most extreme laboratories, even the impossible becomes routine. Now let's turn our attention to something that bends not just space, but our very understanding of what's possible. In these sextuple systems, the combined gravity of six stars creates something extraordinary, a natural magnifying glass on a cosmic scale. This is the gravity lens effect, where the collective pull of all those stars warps space-time so dramatically that light from distant objects gets bent and amplified, like a telescope crafted by the universe itself. Here's how it works. Imagine light from a faraway galaxy traveling across the cosmos, only to pass near a sextuple star system. The combined gravitational field of those six stars acts like a giant lens, curving the path of that light toward us. The result, the background object, whether it's a galaxy, quasar, or another star, appears distorted, brighter, and sometimes even multiplied into multiple images. Astronomers call this gravitational lensing, and in sextuple systems, the effect is turbocharged. What makes this particularly fascinating is the sheer power of the lens. With 6 stars contributing to the gravitational distortion, the lensing effect can be far more complex and variable than what we see around single stars or even black holes. Some models suggest these systems might produce intricate patterns of light, including rings or arcs that wouldn't form under simpler conditions. And here's the kicker: these natural telescopes can reveal objects otherwise invisible to our instruments. Distant galaxies that would normally be too faint to detect suddenly become observable thanks to the amplifying power of the sextuple system's gravity. This means these chaotic stellar families aren't just cosmic curiosities, they're tools that help us peer deeper into the universe than ever before. While we've observed gravitational lensing around massive objects like galaxy clusters, sextuple systems offer a unique laboratory to study the effect on a smaller, more dynamic scale. Their ever-shifting orbits mean the lens itself changes over time, creating a flickering, evolving window into the distant cosmos. It's a reminder that even in chaos, the universe finds ways to show us the unseen. Just when we thought sextuple star systems couldn't get any stranger, along comes a mystery that baffled astronomers and even sparked wild speculations about alien technology. Picture this: a star in one of these complex systems suddenly begins fading, dimming so dramatically that it seems to vanish before our eyes. This isn't your typical eclipse or stellar variability. The dimming was erratic, unpredictable, and far more extreme than anything natural models could explain. When astronomers first noticed the star's light dropping by nearly 80%, they scrambled for answers. Could it be an unprecedented swarm of dust, a colossal planetary debris field, or, as some daring theorists suggested, could this be evidence of something far more exotic, like an alien megastructure? The idea of alien megastructures isn't as outlandish as it sounds. Scientists have long speculated about hypothetical constructs like Dyson spheres, vast, star-encircling arrays designed to harvest energy. While natural explanations are always more likely, the extreme dimming in this sextuple system forced researchers to at least consider the possibility. After all, if advanced civilizations exist, we're better to harness stellar power than in a system with multiple energy-rich stars. But here's where the mystery deepens. Follow-up observations revealed that the dimming wasn't perfectly consistent, ruling out a solid megastructure. Instead, the star's light flickered in bizarre, asymmetrical patterns, suggesting something even stranger, perhaps enormous, irregular dust clouds or swarms of comet fragments stirred up by the system's chaotic gravity. Whatever the cause, this vanishing star remains one of the most puzzling cases in modern astronomy. It reminds us that even our most advanced telescopes can't always explain what's happening in these stellar mosh pits. Whether natural or just maybe something beyond our current understanding, one thing is certain: the universe loves keeping us guessing. Now, as we turn our gaze to the next cosmic wonder, we find stars that don't just dim unpredictably, they synchronize in ways that defy all expectations. But the cosmic oddities don't stop there. Imagine turning the movements of stars into music. Sounds impossible, right? Well, astronomers have done just that, transforming the gravitational dances of sextuple systems into eerie, beautiful symphonies. Here's how it works. Every star in these tangled systems moves with precision, tracing paths dictated by gravity. Scientists take the speed, position, and rhythm of these orbits and translate them into sound waves. The result, a celestial orchestra unlike anything you've ever heard. Single stars might produce simple tones, but in a sextuple system, the overlapping orbits create layers of harmony and dissonance like 6 instruments playing in chaotic unison. Some systems generate deep, resonant hums as massive stars slowly circle one another. others crackle with high-pitched staccato beats from tightly paired binaries whirling at breakneck speeds. The most complex arrangements even mimic musical phrases, rising and falling in patterns that almost feel composed. Why go through the trouble? These stellar soundtracks aren't just for fun. They help astronomers detect subtle gravitational quirks our eyes might miss. A sudden shift in pitch could reveal an unseen companion or a looming collision. It's like listening to the universe whisper its secrets, and just when you think it can't get any stranger, we're pulled toward another discovery where gravity itself becomes a cosmic sculptor. Now picture this: gravity itself becomes a force so powerful, it bends the fabric of space and time. In the chaos of sextuple star systems, the gravitational tugs between stars don't just create movement, they send ripples across the universe. These distortions, known as gravitational waves, act like a cosmic Richter scale, revealing collisions and mergers happening millions of light years away. Here's what makes these systems so special. When stars orbit this close, their immense gravity warps spacetime, creating waves that travel at the speed of light. Normally, these ripples are faint, but in a sextuple system, the sheer number of stars amplifies the signal. Imagine dropping 6 boulders into a pond instead of one. The resulting waves would be impossible to miss. Future observatories, like the planned Laser Interferometer Space Antenna, could one day tune into these gravitational symphonies. The data would reveal not just the stars' positions, but their fates, like catching 2 stars spiraling toward a violent merger or spotting a hidden black hole lurking in the system. What's even wilder, these waves could expose chirps, short bursts of gravitational energy released when stars finally collide. It's like hearing the universe's heartbeat in real time. And with each pulse, we'd get front-row seats to the most dramatic stellar events imaginable. But the surprises don't end there. Just beyond the reach of our current detectors, another mystery waits, where the very laws of physics might twist into something unrecognizable. Now here's something that defies logic: stellar systems that seem to break the rules of time itself. In certain sextuple star systems, astronomers have spotted stars that shouldn't coexist, some appearing ancient while others look freshly born, all in the same cosmic neighborhood. This paradox throws a wrench into our methods for dating stars. Normally, we determine a star's age by its color, brightness, and chemical makeup. Younger stars burn hotter and bluer, while older ones cool into red giants. But in these systems, stars of the same age display wildly different characteristics. Imagine finding a gray-haired toddler playing alongside a middle-aged adult. It's that baffling. One leading theory suggests extreme gravitational interactions might be to blame. As stars whip around each other in tight orbits, they could steal material from their siblings, rejuvenating themselves with fresh fuel. It's like a cosmic fountain of youth, where one star grows older while another gets a second wind. Another possibility: these systems might be the result of multiple generations of star formation. Gas and dust from an older star's death could collapse to form new stars, creating a celestial family tree with grandparents and grandchildren orbiting side by side. Whatever the cause, these age-defying stars force us to rethink how we measure cosmic time. They're a reminder that in the chaos of sextuple systems, even the most basic rules of stellar life cycles can be rewritten. And just when we think we've figured it all out, the universe hands us another mystery to unravel. But that's not all. These cosmic oddities have more surprises up their sleeves. Picture this: vast, shimmering rings of debris encircling sextuple star systems, wobbling wildly like hula hoops losing momentum. These aren't your ordinary planetary rings. Stretching billions of miles across, they're caught in a gravitational tug of war between multiple stars, creating a dizzying dance of dust and rock. Normally, debris disks around single stars settle into neat, flat plains over time. But in these chaotic systems, the combined pull of 6 stars yanks the material in all directions. The result: rings that tilt, warp, and even flip over entirely. astronomers have observed some that oscillate so violently they resemble spinning tops about to topple. What's truly bizarre is how these disks defy expectations. Some fragments get slingshotted into bizarre, looping orbits, while others collide in spectacular fireworks of cosmic debris. At times, the gravitational chaos even rips apart larger objects, turning them into fresh ring material. It's a relentless cycle of destruction and rebirth, sculpted by the star's relentless pull. And here's the kicker: these wobbly rings might be hiding secrets of their own. Their erratic movements could hint at unseen planets or even failed stars lurking in the shadows, further complicating the gravitational ballet. One thing's certain: in a sextuple system, even the debris refuses to play by the rules. Just when you think you've seen it all, the universe unveils another layer of its infinite strangeness. And speaking of cosmic anomalies, wait until you hear about the next discovery where time itself starts bending in unexpected ways. Now, let's take a detour into the realm of the deeply mysterious, where the fabric of reality itself might be twisting under the influence of these stellar powerhouses. Some theorists propose that sextuple star systems could be cosmic laboratories for something far stranger than just gravity. We're talking about quantum foam, the turbulent, frothy nature of spacetime at the smallest scales, a concept so wild even Einstein would raise an eyebrow. Normally, quantum foam is too subtle to detect, vanishingly small and fleeting. But in the extreme gravitational chaos of a sextuple system, things might be different. Imagine the combined gravity of 6 stars churning spacetime like a stormy ocean. This relentless tug of war could potentially magnify those tiny quantum fluctuations, making them noticeable or at least theoretically possible to infer. What's even more mind-bending, these amplified quantum effects might explain some of the bizarre stability observed in these systems. Like an invisible glue, quantum foam could be smoothing out gravitational instabilities that should otherwise tear the stars apart. It's a stretch, but in a universe where sextuple stars exist, why not? Of course, this remains speculative. No direct evidence yet proves quantum foam plays a role here. But the mere possibility opens doors to new physics, hinting that these systems aren't just breaking rules, they might be rewriting them entirely. And just when you thought reality couldn't get any weirder, the universe has another curveball waiting. Up next, a discovery that flips our understanding of cosmic energy on its head. Now, let's shift our gaze to something that defies the very laws of physics as we know them. Imagine observing a sextuple star system where the energy output doesn't just break the rules, it shatters them entirely. This is the great energy paradox, where these cosmic powerhouses radiate more energy than their stars should theoretically produce. It's like lighting a match and getting an inferno. Scientists are left scratching their heads, wondering where all this extra energy comes from. At first glance, you'd expect the combined light and heat of 6 stars to be immense, but some systems go beyond even those staggering estimates. Telescopes pick up readings that suggest energy levels several times higher than what's possible through nuclear fusion alone. It's as if these stellar families have a hidden generator somewhere, pumping out power that shouldn't exist. One leading theory points to gravitational interactions on an unimaginable scale. The constant tug of war between 6 stars could be converting gravitational energy into radiation at extreme efficiencies, almost like cosmic friction heating up the system. Others speculate about exotic particles or even interactions with dark matter, though these ideas remain firmly in the realm of hypothesis. What's truly fascinating is that this paradox isn't isolated. Multiple sextuple systems exhibit this anomaly, suggesting it might be a feature rather than a fluke. If confirmed, it could force us to rewrite textbooks on stellar physics, revealing processes we've never even considered. And just when you think the universe has shown all its cards, another mystery steps into the spotlight. Brace yourselves, because what comes next pushes the boundaries of magnetic mayhem. But the cosmic surprises don't stop there. Picture this: magnetic fields so twisted and chaotic they turn entire star systems into celestial lightning factories. Welcome to the bizarre world of twisted magnetospheres, where the usual rules of magnetism get tossed out the window. In most star systems, magnetic fields flow in predictable patterns, shaping solar winds and guiding charged particles. But in sextuple systems, the sheer gravitational chaos distorts these fields into knots of unimaginable complexity. Imagine 6 stars, each with its own magnetic personality, constantly pulling and pushing against the others. The result, a tangled web of magnetism so intense it generates stellar lightning storms powerful enough to dwarf anything in our solar system. These aren't just brief flashes. Some systems produce sustained arcs of plasma stretching millions of miles between stars, superheated by magnetic reconnection, a process where field lines snap and reform, releasing colossal bursts of energy. Instruments have detected radio bursts from these events so loud they drown out background noise across entire sectors of space. What's even stranger is how these magnetospheres sync up. Observations suggest that magnetic fields from different stars occasionally lock into temporary harmony, creating synchronized storms that ripple through the system like a cosmic domino effect. It's as if the stars are communicating through some unseen electromagnetic language. Theorists are still piecing together how these systems avoid tearing themselves apart. One idea suggests the braided fields act like shock absorbers, redistributing energy before it becomes catastrophic. Others propose that the storms actually stabilize the system by bleeding off excess energy that would otherwise destabilize orbits. And just when you think magnetism can't get any wilder, wait until you hear what happens when you combine it with something even more elusive. The next discovery will make these lightning storms look like a gentle summer breeze. Now let's turn our attention to one of the most perplexing mysteries hidden within these stellar tangles. Imagine a sextuple star system where everything seems to follow the cosmic rulebook except for one member that refuses to shine. This is the enigma of the Dark Companion, a celestial ghost lurking in plain sight. Unlike its blazing siblings, this shadowy object emits no detectable light, making it nearly invisible against the cosmic backdrop. At first glance, you'd expect a gap or some disruption in the orbits, but no. Its presence is revealed only by the way it tugs gravitationally on its stellar neighbors. So what exactly is this unseen interloper? Theories range from a rogue planet massive enough to influence stars to a failed star known as a brown dwarf. Brown dwarfs are the cosmic in-betweeners, too large to be planets but too small to ignite full stellar fusion. They're faint, emitting only dim infrared glows, which makes spotting them in a system already flooded with starlight like finding a candle in a fireworks display. But there's another, even wilder possibility. What if this dark companion isn't a brown dwarf at all, but something far stranger, like a primordial black hole left over from the early universe? The gravitational fingerprints of this object are unmistakable. Stars nearby wobble as if pulled by an unseen hand, their orbits subtly distorted in ways that can't be explained by visible matter alone. Some researchers speculate this could hint at even weirder physics, like exotic dark matter clumps or other phenomena we've yet to imagine. What's truly mind-bending is how such an object ended up in this elaborate stellar dance. Was it captured, or did it form alongside its bright siblings, only to fade into obscurity? The answer could rewrite our understanding of how complex star systems are born. And just when you think the cosmos can't get any more mysterious, wait until you see what happens when these systems align in ways that defy all odds. The next discovery will make you question whether the universe has a sense of theatrical timing. Now let's take a graceful step into the cosmic dance floor, where gravity choreographs one of the universe's most breathtaking performances. Picture 6 stars moving in perfect harmony, tracing delicate, flower-like patterns across the void over centuries, a celestial ballet more intricate than any human masterpiece. What makes this system so mesmerizing isn't just its complexity, but its sheer beauty. Each star follows its own path, yet together they create a synchronized spectacle, weaving in and out like partners in an endless waltz. One pair might spiral inward while another arcs outward, their gravitational pull keeping the entire ensemble balanced. The result is a slow-motion kaleidoscope, with orbits so precise they resemble the petals of a cosmic bloom unfolding over generations. Astronomers call these patterns resonant orbits, where the stars' movements lock into mathematical harmonies. Picture a clock with 6 hands, each ticking at a different speed but perfectly aligned at specific intervals. Some stars complete 2 orbits in the time another takes 3, creating repeating geometric shapes that persist for millennia. It's a gravitational masterpiece, one that could only arise in the rarest of stellar families. But here's the real wonder. These patterns aren't just pretty, they're clues. The stability of this dance hints at an ancient history, suggesting these stars have been bound together since birth, unscathed by the chaos that typically disrupts multi-star systems. Some researchers even compare it to a frozen moment in time, a snapshot of stellar evolution where everything aligns just right. And just when you think the universe has shown you all its wonders, wait until you hear how relativity warps time itself in these systems. The next discovery will bend your perception of reality. Now let's twist our minds around a cosmic quirk that feels straight out of science fiction, time itself bending under the gravitational weight of these stellar giants. Imagine standing on a hypothetical planet in a sextuple star system, where clocks tick at different rates depending on which star's gravity dominates your corner of space. Thanks to Einstein's theory of relativity, the intense pull of 6 massive stars warps spacetime so dramatically that time slows down near the most massive members of the system. Here's how it plays out. A planet orbiting close to a pair of tightly bound, heavyweight stars might experience time crawling just a fraction slower than a world circling the system's outer fringes. Over decades, this tiny difference could add up. An astronaut returning to an outer planet after a mission near the core might find their home world's clocks slightly ahead of their own. It's like cosmic jet lag, but with gravity calling the shots instead of time zones. The most mind-bending part, this isn't just theoretical. We've already measured similar time dilation effects around Earth and our single sun, but in a sextuple system, the variations would be far more extreme. Imagine 2 civilizations evolving on different planets in the same system, their histories gradually slipping out of sync just because of where they orbit. One society might celebrate a millennium while the other clocks only 950 years, and this temporal tango gets even wilder when you consider the stars' motions. As they swing around their shared center of mass, the gravitational landscape shifts, meaning a planet's experience of time could fluctuate over centuries like a universe with its own slow-motion strobe light. Just when you thought these systems couldn't get stranger, wait until we explore how some stars within them might be linked by something even more mysterious than gravity. The next discovery ventures into the quantum realm. Now let's witness a stellar spectacle that defies every expectation, a cosmic escape act so dramatic it unfolds over millennia. Picture this, 3 stars locked in a gravitational tug of war, each fighting to break free while the others cling desperately, their orbits unraveling like a slow-motion explosion. This isn't science fiction, it's the reality of one particular sextuple system where 3 stars are being violently ejected at once, rewriting the rules of celestial mechanics. Here's how the chaos unfolds. In most multi-star systems, a single star might get flung out due to gravitational instability. But in this rare case, 3 stars are simultaneously slingshotting away, their paths diverging like sparks from a firework. Astronomers believe this bizarre event was triggered by a close encounter between 2 tight binary pairs, their gravitational dance spiraling out of control. The energy from that collision didn't just nudge one star loose, it sent 3 careening into the void, leaving behind a wounded trio of stars to pick up the pieces. The aftermath is even stranger. As the 3 runaway stars drift apart, they trail glowing streams of plasma behind them, tidal tails stretching across light years like cosmic breadcrumbs marking their escape route. Meanwhile, the remaining stars recoil from the recoil, their orbits permanently altered. It's as if the system itself took a deep breath and then exhaled 3 of its suns into the darkness. What makes this discovery truly mind-bending is the timescale. Unlike a supernova's sudden blast, this ejection plays out over hundreds of thousands of years. From our vantage point, it looks like a paused explosion, stars fleeing at speeds topping 500,000 miles per hour, yet appearing almost frozen in the vastness of space. If humanity lasts long enough, future astronomers might watch these stars vanish one by one into the interstellar abyss. And here's the kicker: simulations suggest this isn't a freak accident. Sextuple systems might routinely self-destruct this way, their complex gravity creating escape routes where none should exist. It's a reminder that even the cosmos has its own version of survival of the fittest stars fighting to stay alive or fleeing for their lives. Just when you think the drama can't escalate, wait until we reveal how some stars in these systems might be hiding secrets darker than the void itself. The next discovery plunges us into shadow, but the strangeness doesn't end there. Let's peel back another layer of these stellar puzzles and examine something even more baffling: stars that shouldn't exist as they are. Imagine a star with a chemical fingerprint that defies all known rules of cosmic chemistry, like finding water burning in a desert. That's exactly what astronomers have stumbled upon in certain sextuple systems, stars harboring elements in their atmospheres that should never coexist, screaming secrets of violent, recent upheavals. Take, for instance, a star drenched in both lithium and beryllium, 2 elements that normally destroy each other under stellar conditions. In most stars, these elements vanish quickly, consumed by nuclear reactions. Yet here they sit side by side like rivals forced to share a room. The only explanation: a cataclysmic thermonuclear event, perhaps a surface explosion or a collision, that dredged these elements up from the star's depths before they could be wiped out. It's as if the star's own chemistry lab blew up and froze in time. Then there's the case of carbon and oxygen existing in extreme imbalances. Normally, these elements stabilize at predictable ratios as stars age. But in these chaotic systems, some stars show carbon levels 10 times higher than expected, while others have almost none. The likely culprit: material stolen during close encounters with sibling stars, or shock waves from nearby stellar explosions literally shaking the elements into unnatural arrangements. These stars aren't just odd, they're cosmic crime scenes, their atmospheres preserving evidence of recent celestial violence. The weirdest part: some of these chemical anomalies vanish within decades, far faster than standard stellar evolution allows. It's as if these stars are temporarily glitching, their outer layers reshuffled by forces we're only beginning to understand. One theory suggests magnetic upheavals, where twisted fields launch pockets of chemically distinct material to the surface. Another points to stellar cannibalism, stars grazing on material from neighbors and briefly wearing their chemical fingerprints like celestial disguises. Now shift your gaze to the bigger picture. These aren't just quirks, they're clues. Each unbalanced element is a timestamp, a way to reconstruct the system's recent history of collisions, explosions, and near misses. And when we piece them together, a startling truth emerges. Sextuple systems aren't just chaotic, they're alive, constantly rewriting their own chemistry in real time. Just when you thought the cosmos couldn't get any stranger, hold on, because the next discovery takes precision to an almost unreal level. A celestial lineup so perfect it defies probability. Now let's turn our attention to something that feels almost choreographed by the cosmos itself. A rare celestial event so precise it borders on the impossible. Picture this, all 6 stars in a sextuple system lining up perfectly from our vantage point on Earth, like cosmic billiard balls frozen in a flawless straight line. The odds of such an alignment are astronomically low, yet in the vast chaos of space it happens. This phenomenon occurs when the orbital planes of these multiple stars coincide just right, stacking their paths so that, from our perspective, they appear to form a single, shimmering chain across the sky. The result is a breathtaking stellar lineup where each star eclipses the next in a precise sequence, creating a dazzling light show that can last for weeks. It's as if the universe pressed pause on its usual chaos to deliver a moment of perfect symmetry. What makes this alignment so baffling isn't just its rarity, it's the fact that these stars maintain their delicate dance despite the gravitational chaos around them. Normally, the gravitational tug-of-war in sextuple systems would disrupt such precision. Yet here, against all odds, the stars align, hinting at hidden forces or resonances that keep their orbits in lockstep, at least temporarily. Some theories suggest these alignments might be fleeting, lasting only a few centuries before the system's inherent instability tears them apart. But the real magic lies in what these alignments reveal. When the stars line up, astronomers get a unique opportunity to study their individual properties with unmatched clarity. The eclipses act like a cosmic magnifying glass, allowing scientists to measure stellar sizes, temperatures, and even atmospheres with unprecedented precision. It's as if the universe handed them a perfectly timed experiment, one that could unlock secrets about how these complex systems form and evolve. Yet, as mesmerizing as these alignments are, they also raise a tantalizing question. Is this perfection pure coincidence, or is there some deeper, unseen order governing these seemingly chaotic systems? For now, it remains one of space's most elegant mysteries, a fleeting reminder that even in the wildest corners of the cosmos, there are moments of breathtaking harmony. And just when you think the universe has shown all its cards, it throws another curveball, like a star that refuses to die, reigniting against all odds. But that's a story for another discovery. Here's where things take a turn toward the cosmic resurrection. Imagine a star that cheats death not once, but multiple times, defying everything we know about stellar life cycles. In the tangled gravity of a sextuple system, astronomers have spotted what they call a phoenix star, a fiery enigma that reignites long after it should have burned out. This celestial phoenix's secret lies in the gravitational chaos around it. Normally, stars fade when they exhaust their nuclear fuel, but in these crowded systems, the relentless pull of neighboring stars can compress and reheat a dying star's core, effectively hitting the reset button on its fusion processes. Picture a campfire suddenly roaring back to life because someone tossed on a log, except here, the log is the crushing force of 5 other stars squeezing their sibling back into action. The rebirthing process isn't gentle. Each revival leaves the star increasingly unstable, its outer layers stripped away by gravitational tides or explosive outbursts. Over time, it might shed entire solar masses of material, creating shimmering shrouds of gas that glow under the combined light of its stellar neighbors. These episodes can last for centuries, with the star flickering between brilliance and near obscurity like a cosmic candle in the wind. What fascinates scientists isn't just the star's defiance of death, it's the clues these rebirths offer about extreme stellar evolution. By studying the phoenix star's composition and behavior, researchers can piece together how gravitational forces in sextuple systems might alter the fate of stars entirely. Some even speculate that these interactions could produce exotic stellar hybrids, objects unlike anything we've catalogued before. But perhaps the most haunting question is how long the cycle can last. With each resurrection, the star grows weaker, its fuel reserves dwindling. One day, even the gravitational ingenuity of its system may not be enough to spark another comeback. Until then, the phoenix star burns defiantly, a flickering testament to the universe's ability to rewrite its own rules. And just when you think stellar drama can't get more intense, wait until you hear about the star that swings like a pendulum between two binary pairs, a celestial dance so precise it defies belief. But more on that next. Now let's marvel at a celestial tightrope walker unlike anything else in the cosmos. Picture a lone star suspended between two binary pairs, swinging back and forth with the rhythmic precision of a cosmic pendulum. This isn't science fiction, it's an actual stellar configuration observed in sextuple systems, where gravitational forces achieve an almost impossible balance. What's astonishing is how this star defies expectation by not being torn apart. Normally, such extreme gravitational tugs would spell disaster, but in this case, the star moves along an orbital path that's perfectly calculated between the two binary pairs. Think of it like a ball rolling smoothly through a valley between two hills. The gravitational pull from each binary creates a stable path that guides the star back and forth without letting it crash into either group. Scientists call this phenomenon a hierarchical orbit, where smaller scales of motion exist within larger ones. Here, the pendulum star completes smaller loops around each binary pair while also tracing a grander arc between them. The timing is so precise that astronomers can predict its position centuries in advance, watching as it faithfully follows this gravitational groove etched into spacetime. What makes this dance possible is something called mean motion resonance, a delicate gravitational lockstep where the star's orbital period relates mathematically to the orbits of the binaries. It's similar to how a child on a swing gains momentum when pushed at just the right moment. Except in this case, the pushes come from the combined gravity of 6 stars working in unintentional harmony. The pendulum star also serves as a living gravity detector. Any slight wobble in its path could reveal hidden planets, dark matter clumps, or even disturbances from gravitational waves passing through the system. Some researchers speculate that studying these motions might help us test Einstein's theory of relativity under conditions more extreme than any laboratory could create. But perhaps most mind-bending is how long this cosmic balancing act can last. Current models suggest some pendulum stars might maintain their rhythmic dance for millions of years, a testament to the universe's ability to create order within chaos. Just when we think we've seen it all, stars like these remind us that the cosmos still holds dances we've yet to discover. And speaking of dances, prepare to have your mind stretched even further when we explore how these systems might be producing ripples in spacetime itself. But that's a discovery for another moment. Now let's tune into a cosmic symphony written not in notes but in ripples of spacetime itself. These sextuple star systems aren't just visual spectacles. They might be broadcasting gravitational wave concerts across the universe, waiting for our technology to catch up. Imagine 6 massive stars all moving in complex orbits, constantly tugging and warping the fabric of spacetime around them. Unlike simpler binary systems that produce steady gravitational wave tones, a sextuple system would generate an intricate harmony of overlapping frequencies. It's the difference between a single violin playing and an entire orchestra, with each pair of stars contributing its own gravitational note to the mix. What makes these gravitational waves particularly fascinating is their ever-changing rhythm. As stars swing close together and then apart, the wave frequencies would shift dramatically, creating a kind of cosmic Doppler effect. Some researchers compare it to listening to a record where the speed keeps changing. You'd hear these strange gravitational glissandos rising and falling as different star pairs dominate the signal at different times. Future observatories like the Laser Interferometer Space Antenna, or LISA, might be able to detect these complex waveforms. They could reveal details about the system we can't see with telescopes, like whether any stars have hidden compact companions, or if the orbits are gradually decaying toward eventual collisions. The waves might even carry echoes of past events, like that runaway star we discussed earlier, leaving gravitational ripples in its wake. Here's where it gets truly mind-blowing. Some theorists suggest these systems could produce beats and harmonics unlike anything we've detected before. When gravitational waves from different star pairs interfere with each other, they might create resonant patterns that act like cosmic tuning forks, ringing out information about the system's deepest structure. It's possible we'll discover entirely new categories of gravitational wave phenomena in these ultra-complex environments. While we're waiting for detectors sensitive enough to hear these distant symphonies, computer simulations give us a preview. Models show space-time around these systems would look like a constantly churning ocean, with intersecting wave fronts creating intricate interference patterns. Some of these ripples could even propagate in unexpected directions, warping space in ways that challenge our current understanding of relativity. What's certain is that when we finally tune into these gravitational wave broadcasts, they'll rewrite what we know about extreme astrophysics one space-time ripple at a time. But this cosmic music is just the beginning. Wait until you hear about the role dark matter might play in holding these chaotic systems together. Now consider this cosmic balancing act. What if invisible hands were steadying these chaotic stellar dances? Some of the most stable sextuple star systems might owe their harmony to an unseen force, dark matter. While we still don't fully understand this mysterious substance making up most of the universe's mass, astronomers speculate that dense pockets of it could be acting as gravitational anchors in these extreme environments. Picture dark matter as invisible scaffolding woven between the stars. In places where multiple stars orbit precariously close, traditional physics predicts they should tear each other apart or fling one another into space. Yet some systems persist with uncanny stability. The leading theory suggests concentrated dark matter, perhaps in halos or filaments, could provide just enough extra gravitational glue to keep everything in place. It's like having hidden counterweights on a spinning mobile, subtly balancing forces we can't directly see. The math gets fascinating here. Computer models show that if certain sextuple systems contain just 10% more mass than their visible stars account for distributed in specific dark matter configurations, their orbits would suddenly make sense. This missing mass wouldn't just float randomly. Simulations suggest it would need to cluster near orbital resonance points, places where stars repeatedly align. These dark matter knots would then act like traffic cops, gently nudging stars back into stable paths whenever their motions grow too erratic. There's tantalizing indirect evidence too. Some sextuple systems exhibit slight but unexplained timing variations in their eclipses, as if unseen masses were subtly bending starlight along the way. Other systems show stars moving fractionally slower at certain orbital points, like they're pushing through invisible molasses. Both could be signatures of dark matter's subtle gravitational influence. The implications stretch beyond astronomy. If proven, these systems would become natural laboratories for studying dark matter's properties. Do its particles interact with each other? Does it clump differently around multiple stars versus single stars? Unlike underground detectors struggling to catch sporadic dark matter particles, entire sextuple systems might reveal its large-scale behavior through gravitational fingerprints. Yet mysteries remain. If dark matter stabilizes some systems, why do others with similar configurations still fly apart? Perhaps the answer lies in varying dark matter densities across galaxies, or different types of dark matter behaving uniquely in extreme gravitational environments. Future telescopes mapping gravitational lensing around these systems might finally spot the telltale warping that gives dark matter's presence away. What's certain is this: if dark matter does anchor these stellar chaos factories, it would solve one cosmic riddle while opening doors to even deeper questions about the invisible architecture shaping our universe. But speaking of cosmic architecture, our next discovery reveals how these systems might be connected by something even stranger: quantum links spanning light years. But here's where things get truly bizarre. What if the stars in these systems are connected not just by gravity, but by something far stranger? scientists have floated a radical idea that stars in sextuple systems might be quantum entangled across astronomical distances. This isn't science fiction, it's a real hypothesis pushing the boundaries of what we know about the universe. Quantum entanglement, that spooky phenomenon where particles instantly influence each other no matter how far apart they are, might not be limited to tiny particles in labs. Some theorists suggest the extreme gravitational environments in sextuple systems could create conditions where entire stars share quantum connections. Picture two stars billions of miles apart somehow, feeling each other's changes instantaneously, faster than light could travel between them. The math behind this is mind-bending. Normally, quantum effects disappear at large scales, a principle called decoherence. But in these dense star systems, the constant gravitational interactions might preserve quantum states that would otherwise collapse. It's like having 6 tuning forks constantly vibrating together, never losing their synchronization despite the chaos around them. One striking prediction: if entanglement exists, we might spot impossible correlations between stars. Imagine two stars flaring in perfect unison despite being too far apart for light to have carried the signal, or spots appearing simultaneously on opposite sides of a system with no physical mechanism linking them. Some astronomers are already sifting through data for these eerie patterns. Of course, this remains highly speculative. Mainstream physics says large objects like stars should decohere almost instantly. But sextuple systems, with their extreme conditions, might be the exceptions that rewrite the rules. If proven, it would mean the universe maintains invisible threads tying stars together in ways Einstein himself called spooky. Whether this wild hypothesis holds up or not, it shows how sextuple star systems keep challenging our understanding of reality. And speaking of reality-bending phenomena, our final discovery reveals the ultimate fate awaiting these cosmic oddities. Will they dissolve, collide, or transform into something entirely new? Now let's peer into the distant future, what ultimately awaits these dazzling but unstable cosmic dances. Sextuple star systems, for all their intricate beauty, are destined for dramatic endings over timescales that dwarf human history. The fate of each system hinges on a delicate balance between gravity's pull and the chaotic nudges from neighboring stars. Some systems may slowly unravel, their gravitational bonds weakening until one or more stars break free, drifting into the void as lonely runaways. Imagine a stellar sibling ejected every few million years, leaving behind a simpler, but no less strange system each time. Other sextuples could face a far more violent destiny. When stars orbit this close, even tiny gravitational shifts might send them spiraling into catastrophic collisions. Picture two suns merging in a fiery explosion, their debris swirling around the surviving stars in glowing disks of molten material. Then there's the rarest possibility, a graceful transformation. A handful of these systems might stabilize into tighter, long-lasting configurations, like hierarchical quadruples with two tightly bound binaries at their core. Over billions of years, stellar evolution takes its toll. Massive stars explode as supernovae, leaving behind neutron stars or black holes that continue the gravitational waltz. In one hypothetical scenario, a sextuple system could evolve into a bizarre mix of stellar corpses and living stars, a cosmic graveyard where white dwarfs, neutron stars, and black holes orbit in an eerie, silent ballet. The wild-card planetary survivors, if any planets manage to form in these chaotic environments, their skies would transform beyond recognition as stars vanish, collide, or explode. A world orbiting a future black hole might witness its remaining suns circling the abyss in a slow-motion spiral of doom. No matter their path, these systems remind us that the universe is never static. What looks like a perfect celestial clockwork today may tomorrow become a scene of cosmic demolition or rebirth. And with that, We've journeyed through all 50 of these mind-bending discoveries, each revealing how sextuple star systems defy the ordinary at every turn. Which of these cosmic oddities left you the most awestruck? Let us know in the comments, and don't forget to like, subscribe, and hit the notification bell so you never miss our deep dives into the universe's greatest mysteries. Until next time, keep looking up. As we wrap up this cosmic journey, let's take a moment to reflect on just how astonishing sextuple star systems truly are. These celestial marvels have shattered our expectations, revealing a universe far stranger than we ever imagined. From stars dancing in perfect mathematical harmony to rogue suns violently ejected into space, each discovery has rewritten the rules of stellar behavior. These systems challenge everything we thought we knew about gravity, star formation, and even the boundaries of physics itself. Think about it. Some of these stars orbit so close they nearly touch, defying the very limits of stellar survival. Others create dazzling eclipse chains that last for months, turning the cosmos into a celestial light show. And who could forget the bizarre vampire stars siphoning material from their neighbors, or the mysterious dark companions lurking unseen in these systems? Each finding pushes the boundaries of what we consider possible, proving that the universe thrives on complexity and chaos. But here's the real wonder: sextuple star systems are just the beginning. The cosmos is brimming with unsolved riddles waiting to be uncovered. Could there be even more extreme systems out there with 7, 8, or more stars tangled in gravitational knots? What other cosmic oddities lie hidden in the vastness of space, defying our current understanding? Now it's your turn. Which of these 50 discoveries left you the most awestruck? Was it the stars defying the Roche limit, the eerie, zombie star that survived a supernova, or the mind-bending idea of quantum connections across stellar distances? Drop your thoughts in the comments below. We'd love to hear which cosmic mystery captivated you the most. And if you're hungry for more mind-bending space revelations, don't forget to hit that like button, subscribe, and ring the notification bell. The universe is full of secrets, and we're just getting started. Until next time, keep your eyes on the stars, because out there, anything is possible.